It's really a great pleasure for me to introduce to you Fred Lamb, professor here at the University of Illinois since 1970 and a member of our physics and astronomy departments. Fred studied physics as an undergraduate at Caltech, and then he went to Oxford in the UK to study for his PhD. Fred has made many exciting contributions to astrophysics. In the early 1970s, he helped resolve a mystery by showing that bright, pulsing X-ray stars are indeed neutron stars. In the years since, he and his students have explored, at least theoretically, neutron stars, pulsars, white dwarfs, black holes, and other things, including consequences of Einstein's theory of gravity, near stars, and black holes. 17 years ago, Fred helped conceive and plan the X-ray Timing Explorer satellite, which was launched by NASA just a little over a year ago. This morning, Fred has kindly agreed to tell us about exotic objects of the cosmos, neutron stars, pulsars, and black holes. Please join me in giving him a very warm welcome.
Well, good morning. I'm delighted to see you all here. Let's have some fun. I think you should be able to see and understand everything that I'm going to say and do, so I'd like to encourage you, even though you have some notebooks, to just perhaps close them and sit back and focus on what's going on down here. Now, there's something special about neutron stars and black holes. They're almost unique among astrophysical objects in having been predicted by theoretical physicists many years, in fact, decades before they were ever discovered or seen. And they are very compact. Here is a graphic which shows a little bit about them. On the left here is the sun, of course, with a solar mass. If you compare a white dwarf star, which we understand is what happens to a star like our sun when it exhausts all of its nuclear fuel, cools, and contracts, such a star would be just a speck compared to the sun, 1,000 times smaller, and we sort of blew this up here to show the white dwarf star. Now, if we consider a neutron star or a black hole, they are typically having a mass like that of the sun, but are another 1,000 times smaller. So 1,000,000 times smaller than the sun, just specks compared to white dwarfs. A neutron star is like a gigantic atomic nucleus with a mass of the sun, a density like that of atomic nuclei, and dimensions that are like only 10 miles across. A black hole is what happens when you have matter compressed to even higher densities so much that it curves space-time so that radiation and matter cannot escape. A black hole with a mass like that of the sun would have an event horizon from which nothing can escape, which has about the same diameter as the diameter of a neutron star, that is about 10 miles. Many of the properties of these objects have been worked out actually by physicists in the physics department here and astronomy department at the University of Illinois. I just mentioned, besides me and my group, Gordon Boehm, Chris Pethick, David Pines, Jeff Ravenhall, Vijay Pandrapandi, Larry Smarr, Stu Shapiro, Ed Seidel. These are just a few of the people who actually worked out the details and properties of these objects. So we could almost say that you're at the home of neutron stars and black holes. Now let me begin by asking a very basic question. What holds up stars? Matter always attracts other matter. We call that gravity. And indeed, in stars, there's lots of matter. So what's holding them up? Let me just begin by asking about the sun. Maybe I can ask, do any of you know what holds up the sun? Well, let me make an analogy with this beach ball. If I think about gravity, it's sort of like the tension of the outer surface of this ball, which if there was nothing inside would want to collapse it down to nothing. Of course, there's, in our case, also the atmospheric pressure outside, which doesn't exist in space. But let's think of the tension on the surface here as like gravity trying to compress it. When I try and squeeze it, it resists. What's keeping it from collapsing? Somebody. Yes. Yes. You don't know for sure what's inside here, but what might you guess could be inside? Exactly. So it's, in fact, air. Inside there, air molecules are zipping all around, bouncing against the inside surface of this and keeping it from being compressed. So it's the pressure of ordinary hot gas which supports the sun against collapse due to the inpull of gravity. What about neutron stars and black holes? What holds up, say, let's start about a white dwarf. Anybody say what? You know what holds up a white dwarf? Well, it's actually kind of a subtle thing because it's an effect which does not exist in classical physics. It's what we call cold pressure. In quantum mechanics, particles of matter are fermions, and according to the Pauli principle, no two fermions can occupy the same quantum mechanical state. So if I have a gas of cold fermions, like electrons in the case of white dwarfs, and I try to crush it, that would mean that the electrons would have to get closer together and get on top of each other, and that's only allowed if they're not in the same state, which means the electrons, some of them have to go into higher energy states. And so they're zipping around faster. So when they bounce off each other and off the other particles there, they exert a stronger pressure. So this has nothing to do with the thermal pressure. If I cooled a white dwarf down to 0 temperature, it still would not collapse. It's called degeneracy pressure, and it's a completely quantum mechanical effect. There's nothing like it in classical physics. So that's what holds up a white dwarf. It's cold pressure. Now, what about a neutron star? Well, if we go to a neutron star, we think that they are formed, for example, when a white dwarf collapses, and what happens here is we have a fermion electrons in the white dwarf. If we press them together, it's more favorable for them to get together with the protons and combine and to change into a neutron, and then there's a neutrino which goes away. And so you're left with neutrons, almost all neutrons in a neutron star. Actually, that's why they're called neutron stars. Well, these neutrons are also fermions, and so it turns out that if you compress a white dwarf by a factor of 1,000, the electrons go away because they combine with protons. You're left with neutrons, but the neutrons are also fermions, and at a radius of, say, 10 miles, they also resist because of cold pressure. And even if you had a neutron star that was completely cold at 0 temperature, it would still not collapse. Okay, so that's what we think is going on here. So now, if we were to squeeze a neutron star further, so it would support, say, itself, but now if we put on some extra pressure outside and squeezed it, what would support it? Well, it turns out that if you squeeze a neutron star a little bit more, there's nothing that can support it. It collapses and would form a black hole. So let me just summarize here what I've just said. Ordinary stars like our sun are supported by pressure of hot gas. White dwarf stars are supported by cold pressure of electrons. Neutron stars are supported by cold pressure of neutrons. Black holes are supported by nothing. Let me talk for a moment about how neutron stars form. We think neutron stars may form in 2 different ways. One is by collapse of the cores of massive stars in a process that we call supernovae. And let me just give you an example of what we think goes on. If I think about a massive star with a dense stellar core, which when it collapses is going to rebound a little bit, and there's a very extended but very light envelope on the outside. When this star collapses, we get an explosion which blows off the outer lighter part. Something like that. So that's one way we think that you can produce a neutron star. Another is if you have a white dwarf star in a binary system with an ordinary star around it, and they get close enough together, some of the matter will be drawn off the ordinary star, will fall onto the white dwarf, and build up, and eventually the weight will become too great and the white dwarf will collapse, forming a neutron star. Any questions at this point? Well, let me tell you a little bit about the insides of neutron stars. They're pretty strange. Let me mention just a couple of interesting things about them. Inside a neutron star, there's approximately 1 solar mass of neutron superfluid zipping around inside the star with speeds up to 1/10 the speed of light. That's some superfluid. Further inside, there are superconducting protons with a superconducting transition temperature of only about 1 billion degrees. Now, this is really a high-temperature superconductor. In fact, it's the highest transition temperature that we know of anywhere in the universe. The matter at the centers of neutron stars have densities of 10 to the 15 grams per cubic centimeter. That's maybe 5 or 10 times that of the matter density inside ordinary atomic nuclei. And this is the densest matter that we know for sure is present in the universe today. Also, and very interesting for what I'm going to talk about in a couple minutes, many neutron stars have strong magnetic fields, some with fields as strong as 10 to the 13 Gauss. Does anybody know how strong the Earth's magnetic field is? Somebody? 8. Yeah, it's a few Gauss. That's exactly right. So what we're talking about here is a magnetic field that's 1 million times stronger than Earth's magnetic field, a very strong magnetic field. What I've shown down below here is a cross-section of 2 examples of neutron stars. One, if the equation of state is quite stiff, one if it's a lot softer. We're actually not quite sure which of these 2 is closer to the truth. But let me just take you inside from the outside. Neutron stars have a solid outer crust that's shown by this gray area. In the outermost part of the crust, the solid is very much like ordinary terrestrial solids, a lattice of nuclei held in place by Coulomb forces. If you go in further, however, the nuclei become so close together that it's favorable for neutrons to so-called drip out of the nuclei and to flow in between the nuclei through this solid lattice, and those neutrons are thought to be superfluid. This is where the one neutron superfluid moves around inside the crust. If you go in still further, eventually the crust dissolves and you have a fluid core which consists primarily of neutrons but with a small admixture of electrons and protons, and in the very center, we're not sure. Maybe a quark soup, maybe hyperons, maybe some other things, maybe things we don't even know about. So that's a basic overall picture of a neutron star. A lot of that was worked out here at the University of Illinois. Something else that was worked out here is what goes on in the nuclei in the very innermost part of the crust. And this was work that was essentially all done here at Illinois. If you follow in through the crust, the nuclei that we ordinarily have in the laboratory are kind of spherical. And that's what you first encounter as you go down through the crust, and we playfully call those meatballs. We have a sequence we call pasta here, and another antipasta, as I'll explain in a moment. At first, you encounter nuclei like the ordinary ones in our laboratories, which we call meatballs. But if you go denser down, it's favorable for them to form instead long tube-like nuclei, which we call spaghetti. And if you go still deeper, the spaghetti gets together to form plate-like nuclei that we've called lasagna. And if you go still deeper into neutron star, it's favorable for the lasagna to turn inside out. So what you have is where the lasagna used to be, there's nothing, and in between is the anti-lasagna. You go still further, it's favorable to form anti-spaghetti. So you have all of space almost filled by neutrons and protons, but there are little tube-like holes that run through this material. And if you go still further, then eventually you get what we call Swiss cheese, which is sort of the opposite of meatballs. Again, almost all the space is filled by neutrons and protons, but there are these spherical holes. And if you go still further, then all of space is filled, and that's where the crust dissolves. So it's kind of fun. Neutron stars are relativistic stars, so general relativity is important for them. And I think one way that we like to summarize Einstein's theory of gravity is in 2 steps. One step, matter curves space-time, and in the second step, space-time tells matter how to move. So if you have these 2 ideas, then I think you've got an idea of the essence of Einstein's theory. Now let me ask, how could you tell if space was curved? Any ideas? Well, we think that we're outside a gravitating body of the Earth right now, so maybe you didn't notice this morning as you came in, but space here is curved. Not too strongly, not at all like near a neutron star, but how could you tell? You're kind of used to it. Well, let's think about it for a moment. Suppose we consider, instead of 3 or 4 space, something easier, 2 space, what we call a surface. So this blackboard here is a surface. So let me construct a triangle on this surface. And let's think about what happens if you add up all these 3 angles. This is a Euclidean flat surface. So who knows how many degrees there are in all the angles of a triangle? Help me out here. What? 180. You've got it. Okay, so that we're confident about. So I'll just write that down so we can remember that. Now let's think about, instead of a flat surface, a curved surface, like the surface of this, basketball. And let's think about how the angles of a triangle add up in this kind of a surface. Let me see, I need a helper here. Would you help me? I just need a little bit of arithmetic, okay? So what I'd like you to do is I'm going to go around a triangle here and call off 3 angles, and maybe you can help me add them up, okay? So let's start here at the North Pole. Okay, so let's go down to the equator. We have to go along what's called a great circle to do this right. And then we start along the equator. So that's 90 degrees. Can you keep that in mind? Okay, so let's go around here. And now we want to make a closed path, you see, like that triangle there. So now we start north again, so there's another 90 degrees. How many is that? 180? Exactly. Okay, good. Now let's keep that in mind. So we go back north here to where we started and go around this corner. That's another 90 degrees. 270. Perfect. Okay, so what we found out was on this 2-dimensional surface, if you add up the angles of a triangle, the interior angles are 270 degrees, okay? And that's one way that you can tell that this surface is curved, okay? In fact, there's a theorem which tells you that if you go around a closed path like that, add up all the angles and divide by the area, that gives you the mean curvature of that surface. It's called the Gauss-Bonnet theorem. So this is a way to do it. If you don't have a finger, you can use better light rays or particles to trace out what look like straight lines and measure up the angles that way. So that's how we could tell if we're in curved space. Now, actually, I'll use this to make a point. If we were living on this surface and we were only 2-dimensional, we'd have a bit of a hard time not so easily visualizing what's going on here. You're in 4 space and maybe it's hard for you to visualize that. What we've done here, in essence, is take this 2-dimensional surface and embed it in hyperspace. That is a 3-dimensional space. So this, we're living in 3 space. You maybe didn't realize you were in hyperspace, but relative to 2 dimensions, you are. And it's much easier to visualize this surface as being curved when we've embedded it in a larger dimension that is in 3 space. Now, it's helpful in thinking about the curved space outside, say, a neutron star or black hole to do something similar, but we have a problem in that we have basically, if you have time development, 4 dimensions, or if things are not developing in time, you still have 3 dimensions to worry about, and we only live in 3 space, at least as far as I know. So we can't, easily embed 3 space in 4 space. That's not what we're in. So what we need to do is to suppress one of the dimensions. So the usual thing we do, like if we're talking about a sphere, is we keep the radius, okay, and the azimuth, but we say suppress one of the other directions, like the angle between North Pole and the equator. And then what you do is you embed that curved space in 3 space, and we can sort of see it, and that's actually what we have a model of here. So if you have like a neutron star or a black hole, which curves space around it, we embed that in 3-dimensional space, then the radius is along here, okay, and the azimuth is along here, and we've suppressed the north-south dimension. So we can do it in 3 space. So one of the things I'd like to call your attention to is that the way to measure the radius here is to go along here, okay? And I think you can see that the circumference here is actually a lot less than 2 pi times this radius, okay? If I did 2 pi times this, I'd be, okay? So that's another indication that this is an example of a curved surface. And if you have matter like the star curving space, and you have that curved space telling matter how to move, then you get matter, say, moving in orbit. And eventually, the matter will fall down onto the surface of, say, the neutron star, or if it's a black hole, it will just fall out of our universe. Okay, well, I talked a little bit about what the physics of neutron stars is like. Let's talk about what neutron stars look like when we around Earth and look out there to see what we can see. Let's go visit 3 different types of neutron stars very briefly, a kind of quick Cook's tour. Rotation-powered pulsars, like the famous Crab pulsar, put out regularly pulse beams of radio emission. Then there's something called accretion-powered pulsars, matter falling down onto a neutron star, comes in screaming into the neutron star at nearly the speed of light, slams into the neutron star surface, is heated to billions of degrees, and radiates primarily in X-rays. There's another kind of neutron star that we see, so-called X-ray burst sources. Here, the matter that's fallen down on the neutron star has cooled and been buried, and it sits there, but gradually it builds up, and eventually a gigantic thermonuclear explosion occurs, which puts out an enormous burst of X-rays, a billion times more energy than the largest nuclear explosion that's ever exploded on Earth. And we see a huge flash of X-rays, and during that time, the star puts out an amount of energy that's 1,000,000 times more than that of the sun every second. So let me just keep track of this over here. Let me talk about the discovery of radio pulsars. It's kind of an interesting story. Back in 1967, Tony Hewish at Cambridge University in England and his student Jocelyn Bell built a new telescope with the idea of studying something called the twinkling of radio stars. Now, if you go out at night and look at ordinary stars with your eye, I think you've all noticed that they twinkle. Well, it turns out that radio stars also twinkle, but whereas the stars that we can see with our eyes twinkle maybe, every second or so, or a little faster, the radio stars twinkle on time scales of weeks. So they thought they'd study this because it would be a good way to learn about the gas between the stars. And they built this radio telescope. It doesn't look much like an ordinary telescope. And actually, it was pretty low tech, even at that time. It's kind of like a glorified chicken coop. Okay, so here they were out on the marshes outside Cambridge, putting up these poles, wooden poles, and stringing wires between them, and so on. And the summer of 1967, they finally got it finished. And they turned it on. And very shortly after that, Jocelyn Bell discovered a signal that they hadn't seen before that appeared about the same time every day. And it looked a lot like interference. In fact, it looked kind of like the signal you might get from a motor car being driven by the antenna every day at about the same time, and there's something wrong with the distributor, so it goes sort of pop, pop like that as it goes by as the cylinders fire. In fact, That's the first thing they thought of. And they thought, well, this person's coming to work every day at 9 a.m., so every day at 9 a.m., you get this interference signal, and at first they were kind of annoyed. Well, the signal then went away. Turns out later they realized that it was because it was twinkling. It went away for several nights, and then it came back. And they hooked up a better recorder. This is actually the original record from the chart recorder. And if you look at with a better recorder, you see, wow, some regular pulses. And they studied these, and they found out that it came back not exactly the same time every day, but a little bit earlier every day. Now, does anybody have any idea why that might be? It was crucial to notice this. Have you ever heard of the fact that the solar day and the stellar day are not the same? It's because we go around the sun. So if we count when a star comes back to the same spot in the sky, it comes back a little earlier every solar day. And our clocks here on Earth are all set to the solar day. So if we watch when a star rises, it rises a little bit earlier every night. And that's what was happening. So they knew that it was extraterrestrial because it was keeping time not with the sun, which would be something in the solar system, but keeping time instead with the stars. So they knew it was even beyond the sun. And because it was so periodic and pulsing, at first they actually feared it was coming from some extraterrestrial civilization. And at first they kept it very secret because they thought if this got out, then it would cause a panic and there'd never be any real chance for a long time of getting to the bottom of it and figuring out what's going on. But they studied it carefully for several months, and finally they satisfied themselves that it was a natural phenomenon, not little green men, as they called them. And so they sent a paper to Nature, which was published early in 1968, announcing the discovery of these new class of objects, which turned out to be neutron stars, the so-called radio pulsars, or rotation-powered pulsars. Now, an interesting question. Why weren't pulsars discovered before? Now, there's many reasons, but I think two of the main reasons are that radio astronomers simply did not expect signals from cosmic sources to vary very rapidly. I mean, there's this idea that the stars shine, they never change, and so on. Well, it turns out it's not true, but it took a long time for astronomers to really realize that. The other thing is that, as I mentioned, the signals looked a lot like interference. So, in fact, it turns out that after this discovery, it was found that strong radio pulses from pulsars had been recorded many years before, but had not been recognized as coming from extraterrestrial sources. So Jocelyn Bell played a key role in noticing this signal and demanding that Tony Hewish and the others pay attention to it. In fact, this kind of thing has happened many times since. It happened with the discovery of radio pulses from Jupiter, which were ignored for a long time. It happened with cosmic X-ray bursts from neutron stars, which were also ignored for a long time. And there's interesting stories about both of those. Now, this discovery resulted in the Nobel Prize for Tony Hewish. Jocelyn Bell was not a recipient. And this caused an outrage in the scientific community. And I think there's probably at least two main reasons why Jocelyn was not recognized. One, she was a, quote, mere graduate student, unquote, even though it was her stubbornness in insisting that people pay attention to this, which looks like it played a key role in this discovery. And the second thing is, frankly, I think it's partly because she was a woman and not part of the Cambridge establishment. But there was such an outrage about that a second Nobel Prize, which was awarded just a few years ago to another discovery concerning pulsars, was awarded both to Joseph Taylor and to his student, Russell Hulsey, who played a fairly routine but important role in the investigation. So perhaps we made some progress there. The bottom line here, I think there's a moral pay attention. Now, how do rotation-powered pulsars work? Well, what we're thinking about here is a neutron star. We need a magnetic field, so here's the star. We'll think of, say, a dipolar field like this. And we think that there'll be some particles gyrating here and producing radiation coming out along the magnetic axis. So what I'd like you to think about with me is what's needed in order to make not just radiation, but a pulsar. And so I need an assistant here. Let's see. How about you? So come on down here. You're going to be our pulsar. Now, just to reassure the audience, because I'm going to ask for some other volunteers in a minute, I just want, like in the magician's show, you want to make sure there's nothing here that's been fixed. So just like to reassure the audience that you've never seen me before, right?
No, I'm just your daughter.
Okay, so what I'd like you to do is pretend you're a pulsar. So here's the beam of radiation coming out. Can you hold that? That's so now along the magnetic field. So let's just check with our observers out here. Do you see any pulses? No. Okay. Well, this isn't enough. Okay. Now, maybe if we spin you. Okay. So we have a spinning neutron star. Do you see any pulses? Yes. Very strong? No. Okay. Well, let's try something else. Let's tilt the magnetic axis relative to the spin axis, and now we'll spin you. Okay. Anybody see pulses? Yeah. Okay, great. You're a great pulsar. You can take your seat now. Let's have a bit of applause. So, what we've learned is that there are three key ingredients here. We need a spinning star, and it turns out if you go into the physics, it has to be rapidly spinning. You need a strong enough magnetic field to make the radiation, turns out about 10 to the 11 Gauss. And the magnetic axis must be tilted with respect to the spin axis, otherwise you don't get any pulsing. So I'd like to share with you what three pulsars kind of sound like. Now, of course, you actually can't hear pulsars. They put out radio emission, and we're used to hearing acoustic waves. But what's been done here is my friend Dick Manchester put a tape recorder on his radio telescope and converted the radio waves into sound waves so that we could hear them. So what I'm going to show you, let you listen to are the recordings from three pulsars. These are their telephone numbers. The first one is spinning 0.7 second period. The next one, a quarter of a second. And this is the famous Vela pulsar at 89 milliseconds. And let you listen to what this sounds like. Now, if you listen carefully, you can hear occasional double peaks. So you usually get one pulse, but occasionally you get pop-up. It's kind of like a heartbeat. But remember, this object has the mass of the sun, and it's like the size of Champaign-Urbana, and it's spinning that fast. Now, 0950, one of the first pulsars discovered, and I think you can understand that at first it sounded quite a lot like interference. Comes and goes. Could be a motor car idling, right? Here's the Vela pulsar. It's all because of missing pulses. Syncopation. Okay, I always can't resist after this taking a vote. How many like the first pulsar the best? The second? The Vela pulsar. Yes, okay. Let's hear it for Vela. It's kind of unfair because the same one always wins. But anyway. Okay, well, let's talk about accretion-powered pulsars. Now, here we're talking about matter falling onto a neutron star. Just like before, we need a spin, but because it's not rotation-powered, the rate of spin doesn't matter. Anything is fine, as long as it's spinning a little. We need, again, a strong magnetic field to make a beam of radiation. And again, like we talked about before, the magnetic axis must be tilted with respect to the spin axis. But we need something else. We need an adequate supply of matter, because the way these neutron stars are powered, matter is being sucked off a companion star, maybe occasionally from the interstellar medium, but usually a companion star as far as we know, and falls down onto the neutron star, crashing into the surface, getting heated to 1 billion degrees, and putting out X-rays. So you've got to have an adequate supply of matter, and in essentially all cases that we know about, that seems to be provided by a companion star. And theoretically, we said there must be a companion star. Now the question is, how would you know? What could you see that would help you determine whether or not there's a companion star there? Now here I need some more help. So let's see. Doesn't help to sit in the back, actually, you know. Would you help me? Would you be a pulsar for me? Okay, and I need another helper. Would you be my second helper? Are you willing? It's, I think, pretty safe. There's X-rays flying about, but only in our minds. Okay, so this is kind of like a little choreography, so it's not very easy. So we'll practice a little bit. So like before, so if you could just wait in the wings here for a moment, okay? So let's practice being a pulsar. So here's your beam of, now this is X-rays, not radio waves. So now see if you can, which is easier, which way to turn for you? Okay, so do you want to turn this way? So just try and stay in the same place and spin like that. Great. Can you see the pulses? Okay, so now, so I'm going to, in a minute, ask you to continue doing that. But if you feel like you're about to fall down, you can slow down or stop, okay? Okay, now, here we have our companion star, okay? So it's a big, massive companion star here. Now, what we're going to do is we're going to ask you to orbit around the pulsar. So just wait for a minute. Let's practice that. So maybe you want to get in a little closer, but you can just walk around here a little closer. Yeah, so okay, so that's what's going to happen. Now we're going to ask if you were, and now there's an important point here. Because this star is kind of massive, it's gravitating, so really we need a choreography where you walk around each other. Can you do that? Okay, now, so just walk around each other, because that's what really happens, right? Okay. Okay, this is going to be really hard. So now, just so you visualize that, I'm going to ask you to stay still, but imagine she's walking around a bit too. Can you just spin and you walk around and you tell me what you see that if you were an observer, like we are on Earth far away, might tip you off that you have a companion star. What happened right there? Yes, in the back. Exactly. So we have a periodic eclipse. Every time the massive star is in front between us and the X-ray pulsar, we don't see the pulses. Great. Keep going. What else might you see? Yes. Yes. Beautiful. Now, it turns out the X-rays don't reflect very well, but in real life, what happens is every time this X-ray beam hits the star, it makes a little visible light, and a pulse of visible light comes off the companion star, and we can see that with our ground-based optical telescopes. We can time it, and we can see that the light, we can measure the light travel time from the neutron star bouncing off here and coming to us, which takes a bit longer, for example, here, than the radiation that comes directly. And we can watch that relative timing exactly, and we can see, wow, there's something reflecting that's going around the neutron star. There's more. What else? Any other ideas? Well, suppose you're this poor, big companion star, but poor big companion star. Zap, you get zapped with X-rays right there. Zap, you get zapped with X-rays. Zap. What do you think might happen to you? Now, let me remind you that the power of these X-rays coming off is 1,000,000 times the power of the sun, entirely in X-rays. And by the way, it's not coming from the whole surface of the neutron star. It's coming from an area that's only about as big as the quad over here. 1,000,000 times the power of the sun. And that is zapping this companion star. What might happen? Pardon? Yeah. So your side here that's near this neutron star is going to get very hot. Okay? And it turns out that, I'll do this because this is what really happens. The stars usually go around with keeping the same face to the neutron star. This face gets very hot. And so when companions like you are behind this star, this heated face is bright. Now you go around like I was doing. And now you're between the observer and the star. His back is cold. You know, it's like when you're in front of the fireplace. Okay, you can see that. So you see, wow, there's this funny optical star up there that's, you know, turning on and off. It's bright and dim, and exactly the right rate to match up with this reflection bit. Okay? And the eclipses, this periodic. Now there's one more thing. Okay, keep going. Now this time, just you can walk around. You don't have to spin, just walk around them a bit. What happens if this neutron star is moving around in a circle? Trains, ding, 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 ding. Doppler, great, you got it. So these pulses are coming out regularly from this pulsar, but because the pulsar is moving away from us and then toward it, the pulses temporarily slow down and speed up, and it's all got to go together. We have to, to know that this is a companion star orbiting a pulsar. It all fits together, and it turns out it does. So thank you very much, a wonderful pulsar, and thank you for your companionship. So, just to summarize, here's how we can tell that we are, in fact, dealing with a neutron star in a binary system. Now, there's a small problem that I haven't told you about so far, and that is that X-rays, while they can go through your teeth, can't come through the Earth's atmosphere. It turns out there's more X-ray absorbing matter between us and the top of the atmosphere than in your teeth. So the only way that we can observe this X-ray pulsar and the X-ray burst that I was telling you about is by going into space. And what we've used are Earth satellites. Suspected neutron stars and black holes were discovered by Earth satellites in the early 1970s. And about 18 years ago now, in 1979, another professor here at the University of Illinois, David Pines, and I led a workshop which came up with the concept and plan for a special satellite that would focus on the questions having to do with what's happening right at the surfaces of neutron stars, right near the event horizons of black holes. And we didn't realize how long it was going to take us to get that satellite up, but it's called the X-ray Timing Explorer. It was launched about a year ago, and I just want to share that launch with you for fun. It was launched on a Delta II launch vehicle, and let me preview what's going to happen, because at first not much happens, and then everything happens all at once. So one thing you need to know is this rocket has 9 strap-on solid rocket motors. And the key here is you got to light the main engine before you light the solids, because once the solids are lit, you can't turn them off. Okay? So this is kind of a little hairy. Another thing what you will see in the video is that there's some cloud cover. I'll talk about that in just a minute, so make it a little bit hard at one point to see. But let me say that there were 6 failed launch attempts for this mission on this Delta. And on December 30th, it was a picture-perfect launch. I woke up my whole family by yelling and clapping as the rocket cleared the launch pad. So I'm going to show you that launch now just for fun. And what you'll see is the build-up to it, nothing much happening, then everything happens at once. First the main engine starts, then the solid rockets. Then what happens is after it's gotten to about 10 nautical miles, the strap-on solids, the bolts blow with pyro bolts, and the solids, you'll see them peeling away, and we're really underway. Everything's going great. So let's take a look at this. So we're listening. But we've been here before, right? So I was listening on the telephone. I couldn't see this. So even now, when I listen to this, I get goosebumps. Because it's like 17 years of work, $250 million on the line. This is the most reliable rocket the U.S. has, but one of these just blew up about a week ago. You probably saw it on the evening news. The range safety officer came in with the clearance to go. As we get really close to launch, you'll hear at T-minus 5 seconds, they call out green board, which means all the lights on the launch control panel are green, which is what you're waiting to hear. There's one red light. We go into the clouds here, so you're just trying to track.
We're coming into the Mach 1 time frame here. Okay, now 5 solids burning. The solids are beginning to tail off, and we. Let's see, are you performing? Roger that, let's see. Out.
So now it turns out that just a few weeks before that, by the way, I've put into your packet a World Wide Web address where you can follow the mission progress, that there was a new type of object that appeared on December 2nd, a year ago, doing something that had never been seen before. Namely, it was both producing pulses and gigantic X-ray bursts. And because this thing was doing so many different things, not only those, but some other things that I'll show you in just a second, we called it the one-man band, the X-ray one-man band, to try to explain it to the public and to the media, and they really liked that, so that you find that took off, and you can find it all around. We still don't know what caused this star to appear in a giant outburst that lasted over 5 or 6 months. It produces a giant burst every few seconds of X-rays. There's more total energy in each burst than in the total power, the total energy that comes out from the sun in a whole week. And it's located near the center of our galaxy, but even that far away, it's by far the brightest X-ray star in the sky. Well, the BATSI team, the Burst and Transient Explorer team came in on Monday morning, and they looked at the records from over the weekend. They said, what the heck is this? Okay? It was picked up by this special instrument that's out there, sort of like the National Guard. It never sleeps. You know, it's sort of looking at the whole sky for unexpected events, and it saw this thing turn on. Okay? And a telegram flashed out around the world to all the observatories to look at it. try and figure out what's going on. There was a problem because when it first turned on, it was almost right behind the sun from our point of view. And so most telescopes could not look at it. And so it was several weeks, 6 weeks or so, before it got far enough away as we go around the sun to be able to use other telescopes. And fortunately, the X-ray Timing Explorer was launched just during that period. So just when it got far enough away from the sun to look at with other instruments, we were able to go and look at it. And the X-ray Timing Explorer did a lot of work in figuring out what it is. Now, I personally have slightly the feeling that it's taunting us, because every time we thought we had it figured out, it did something different that we couldn't explain, okay? And this behavior is continued. I think there may be intelligent life, maybe with a sense of humor, because it happened on December 2nd. It turned on. This year, my graduate student called me at 9:30 in the evening. He said, "Fred, what's going on?" He said, "I just got this flash, and it looks like somebody accidentally put out the same telegram that came out this same day last year, that this new source turned on." And I said, "What?" And he said, "But I looked at it more carefully, and it's not exactly word for word the same. But it turns out this bursting pulsar died away, and then on December 2nd, again, exactly 1 year later, it turned on again and did exactly the same routine, okay? And we still don't understand why. So there's an unsolved mystery. I would say, just to call your attention, there's a packet of additional information for your notebooks at the back of the room that you can pick up as you leave, because it has the answers to some of the things that I was asking about, so I kind of kept it back until the end, but also has a bibliography and some other information about the bursting pulsar. Let me turn to the conclusion here about what happens if we squeeze a neutron star. We get a pressure of cold neutrons that increases, but the gravitational force increases even faster. And so what happens is eventually the star collapses to a black hole. And that's a place where the curvature of space-time is so strong that not radiation or matter can escape. So we think black holes may form in 3 ways. The collapse of the cores of massive stars, more massive than form neutron stars. Accretion of matter onto neutron stars. If you just keep piling matter on, eventually the neutron star cannot support itself against gravity, and it collapses to form a black hole. And then finally, the coalescence of orbiting neutron stars. So this is the opening segment for a PBS documentary on this object, which was put together and shown last year on PBS TV. Let me just say a couple more words here at closing on black holes. They have a definite edge. You cannot see inside. If they're spinning like neutron stars, they drag the space nearby in a kind of swirling motion like a tornado. And we say they have no hair, by which we mean that a black hole can be characterized completely by just 3 numbers: its mass, its angular momentum, and its electrical charge. But for astrophysical reasons, the electrical charge is usually negligible, so there are really just 2 numbers that characterize any black hole. So it doesn't matter whether they're formed from collapsing stars, by throwing together refrigerators, from cars, or even Illinois soybeans. In the end, there's only really 2 main numbers, the mass and the angular momentum, that determine the properties. Now, let me just mention that there are several places where we think we see black holes, namely in binary systems, where, like the neutron stars, they're going around a companion star and matter's being pulled off the companion star, swirling into the black hole, producing enormous X-ray power. We also see what we think are supermassive black holes with masses not that of the sun, but 1 million or 100 million times the mass of the sun at the centers of galaxies, which we call active galaxies, active galactic nuclei, or quasars. And so those are some of the places where we think we see these black holes. Now, in binary systems, here's kind of a sketch of how the black hole here might draw off gas from the companion star, which then winds its way down just like the metal ball did here. And as it winds its way down, the friction heats up the gas to millions or billions of degrees and produces X-rays. If we have a supermassive black hole in the center of a galaxy, there's a problem, because that's presumably been there for quite a long time, and it's been sucking up all the gas and stars in its neighborhood for millions and billions of years. So there ought not to be anything left there to suck up and to make X-rays and radiation from. But yet we see these very powerful quasars putting out powers that are 1 million or even 100 million times the power of the sun from one object. So how might that happen? Well, again, a number of people are working on this project, and Susan Lamb here at the University of Illinois has been one of those. And I just show you a short video which will maybe give you some idea of how this might happen. How can we power a black hole that's been there for a long time? So does that give you some idea of what might happen? These calculations were carried out by Susan with her student Richard Gerber and postdoctoral student Dinshaw Balsara here at the University of Illinois, and then rendered into this IMAX format using the supercomputers at the National Center here on campus. So what it suggests is, and what they've suggested, is that what's happening is that even though matter may have been sucked from around a black hole in the past, when two galaxies collide, everything is so disturbed that new matter is scattered and drawn and forced into the area around the black hole, which gives it new life. And that's what's causing black holes to be turning on and burning brightly today. So that's where I'd like to stop and just say in closing, by the way, that Hubble space photographs have shown just in the last few months that almost all quasars that we can see nearby us are in galaxies that are colliding with other galaxies. There are many things about neutron stars and black holes that remain still to be figured out, and I hope that maybe some of you will help us discover the answers to these questions about the exotic objects of the cosmos. Thanks for your attention.